Okay, so this afternoon's session is supposed to talk a little bit about reproducibility and reproducible workflows. And so I thought I'd spend a few minutes kind of talking about reproducibility while the hub comes online. And then, if the hub doesn't come online, I hear that you have Docker installed on all your laptops. I'm not going to look at these guys. I'm just going to hold the blinder like this. So as scientists, we see this thing. This has been one of my favorite XKCD cartoons for a long time. We want to see that something keeps happening. To me, that's really the sense of reproducibility, that if we do something, we expect to see certain patterns. If we don't get that pattern again, then we think about what are the differences that cause the change in pattern. But it turns out that in science, things are not necessarily very reproducible. So this is an example of locations of white matter deficits between people who stutter and people who don't stutter. And I'm sure if you look at the locations, you will say, there is no consistent pattern in this figure. But that's the state of science right now. Yet when people write about this, they often write about white matter deficits being under the left ventral motor cortex, premotor cortex. But that doesn't come out from the actual figure when you plot all the points that they show as being different in the papers that are out there. I'll take another example. So this was Josh Karp taking a particular data set and analyzing it with many different workflows. And at the end of each workflow, this is an fMRI contrast, he points the peak coordinates of the results on a brain. If every workflow gave the same result, I would expect these points to be clustered together in very localized settings. But that's not quite the case. Did you have a question? Oh, okay. So there's variation in activity based on analysis pathways. More recently, work from Tom Nichols and others have shown that the different models that we use in our various dominant analysis software are actually different. The error models are different across SPM, AFNI, and FSL in how we do GLM type analysis. So we would expect by that difference to get differences across these things, but we don't necessarily run our analysis across these three types of software most of the time. We choose one and stick with it, often because our lab uses it or somebody told us that this is the software we should use. Finally, there are interactions. So this is looking at prediction of age and gender in a cohort using processing that was done either through ANS or through FreeSurfer. And this is using machine learning based on features extracted from either of those two, and you can see distributions in results that come out as a result of the different kinds of processing. So what software tool we use also has differences across targeted applications. What this is the same data set run through FSL's FAST and FIRST, which are tools that extract volumes of subcortical structures and brain structures like gray matter and white matter. But the difference is, what they did here was they ran the same tool on different OSs. So you would expect these to have the same values, as in they're plotting dice coefficients. I would expect those to be 1 if I got the same result every single time. The fact that these have distributions that are not always peaked at 1 suggests that the underlying operating system has an influence on the exact same tool that you're running. This is a similar analysis using two other operating. In the previous case, it was the same kind of Linux operating system. This is going between Mac OS X and Ubuntu systems. Shows the same exact pattern. And in some cases, for certain structures like the amygdala, you get to see about 6 or 7% difference across runs from the same software across two different versions of operating system. So this brings us to what is reproducibility? And I'd like to have a poll over here in some sense. What do people think about when they say reproducible analysis? I know you've heard one lecture on it this week, at least one. JB has no idea, so you guys have to help him out.
No
So when you hear the term reproducibility, what do you think it entails? Yes? Okay, so the same thing that they claim, are you looking at the statement that they make at the end of an analysis?
Sure.
Okay.
I would go to the gold standard.
The gold standard, the full replication? Okay, we'll try to get there. I'm just trying to think about the different ways people think about reproducibility. Yes?
I mean, I would like to see the ability to do the same experiment and come to a similar conclusion, I guess.
Okay.
Learn the same thing.
Okay. I'm going to use a slightly different term for that in a second, but I see that as one way of thinking about reproducibility.
Say a paper called Reproducible, if you gave me enough information to be able to perform the same steps that they performed.
Okay.
May or may not replicate the same result, perform the same steps.
Okay, so reproducing an analysis pathway that's in the paper, and maybe even the experimental protocol to some extent. So this was work by Carol Goebel and her group in kind of thinking about this reproducibility spectrum that you have the publication only. And this is a little old, well, almost 7 or 8 years old at this point in time. The situation is changing. It's not quite there where you start getting code and data available with papers. The typical publication still doesn't have all the pieces necessary. So we kind of redefine this along the following lines, that we think of the spectrum of reproducibility as something that might say, okay, you have the original data, the original analysis, and you get a result. You should be able to take that original data and run the exact same analysis, and within some tolerance, there might be probabilistic methods or other things, get the exact same results. So that's repeatability or re-execution, given the same data, the same analysis. And maybe I can break down the word analysis into two pieces. It involves both the software components as well as the hardware components. Because as many of us know, many of the things we are doing now uses specialized hardware like GPUs or FPGAs to do certain things. And sometimes if somebody gives you something that was run on a specialized hardware, it's hard to repeat it on your own hardware if you don't have the same specific thing. So I think of analysis as bundling hardware and software. Okay, then there's this word, and this is perhaps closer to what Nate was talking about, this generalizability. That one, you could think about generalizability of the analysis pathway. So given the exact same data and nominally similar analysis tools, you get a similar result. Given nominally similar data and the exact same analysis, you get a similar result. And given nominally similar data and nominally similar analysis tools, you get a similar result. Now, I've used the word similar, which is in quotes for a reason, is that there's a lot of wiggle room around what similar means. We have to provide thresholds, tolerances on how close we think things should be. Most things we do in the brain imaging space don't often have ground truth. So similar is something in the eyes of the beholder a little bit. So we will take this as an exercise. Replicate this. My paper concludes increase in resting state connectivity between right superior temporal gyrus and the right superior frontal gyrus in subjects with autism, and this connectivity correlated with diagnostic severity. How does one go about replicating this? So ideas, tosses. What do you need? The data. Okay, so, okay, that's one. What else?
Exact coordinates of the ROI.
How those ROIs are defined, right? Okay. So you need to information on subjects if you don't have access to the data, right? So if you wanted to replicate the actual experiment, you would want to know how that cohort was collected and what the characteristics were. What else? Which measure of connectivity, right? So it says some measure of connectivity was, what else?
To me, the spirit of the question or the spirit of the replication would be less inclined to the specifics of all of these terms and more towards like generally speaking, with some measure of confidence, right? Versus like, otherwise we would need the method section, right? So that's how I take that question.
Okay, so the most generalizable form of this is any measure of connectivity under any definition of these ROIs, under some cohort that describes, this is, I think, yeah, subjects with autism, right? Under some notion of autism diagnosis, under under any scanner or sequence that collected that data, and I should get the same kind of result. Given what we've seen, is that where one would go to the full generalizable extent?
Yeah, I guess. I mean, I think that it would also have to do with like what was the point of this paper, you know, or like what was the point of the result, right?
Well, it's an observation that I see this correlation. We make observations all the time. So now the question is, it's a generalizable observation. Going back to the XKCD thing, lightning strikes, I get a shock. Is this something I can see happen all the time? Yeah. But yes, there are all kinds of pieces of information that one needs to think about how this information generalizes. And the less specific you can be, the more likely that this finding is going to generalize. But that may require multiple studies, multiple data collection efforts, large-scale databases to do so. Okay. So this is kind of rephrasing that spectrum in a couple of different axes. And I think you can look at this from that perspective. So you have the original data set, a similar data set. You have original analysis, similar analysis. And we are going to use these specific terms instead of using the word reproducibility. Whenever I use the term reproducibility, I'll mean any of these things taken together, right? But we can be much more specific about, are we re-executing? Are we replicating? Are we testing robustness? Or are we doing full generalization of things? And I think if we are clear about what we mean, I think that will reduce a lot of the issues people have with when they say, is your research reproducible? Because they're not being very specific about what that means. They mean a lot of things, and I think we can be much more specific about those components. Okay. And for more on reproducibility, you can go to repronym.org, which is a website for a grant that has all kinds of tools and resources that can help with understanding these different facets. Okay. What we wanted to do today, how's the hub doing? Not well. Okay, it's an unwell hub. So let's talk a little bit about the components of reproducibility, at least in an analysis perspective. Okay. So what are the components that you would require to re-execute an analysis? Yes?
Probably the same computing environment.
Same computing environment. Okay. And and by that you mean?
So same hardware, same software, same versions of the software.
Okay, so same hardware, same software, same versions of software. I think that's important, right? If you want re-execution, you want all of those things. What else do you need? I heard that earlier. Somebody said data, right? So you need the exact same data on which you run those same analysis scripts. So if we can learn how to get hold of data, or version data, or look at data, and create environments that are consistent, we're kind of halfway there in terms of being able to re-execute things and to distribute things. And one of the first things I wanted to show was, I will start with at least the description side of things. DataLad. How many people here had never heard of DataLad? Great. That means all of you now have heard of DataLad. You don't know what it does, but you now know that this term exists. So DataLad is, how many people here are now familiar with Git? How many people that totally have no clue what Git is? Fantastic. You guys did a good job. So Git is typically used for versioning code, things in text files, etc. DataLad builds on a software that builds on Git called Git Annex. And Git Annex was built to solve a very simple thing, which is how do I share my MP3 files between my computer at home, my computer at work, and some other devices that I have access to. What it does is it can point to different stores of data, and it can move data between different places. So imagine I have a giant collection of MP3 files. I don't want to copy it to every device I need to listen to it. I might copy only 10 tracks from a file. So Git Annex provides this capability of versioning those MP3 files, or more generally, any file, and allows you to move them between different resources. There's something called the Git Annex Assistant, which acts like Dropbox, syncing things between different stores. So DataLad is built on top of this thing called Git Annex to help version data. But while they built it, they essentially created a different kinds of features that are extremely useful to us doing research. You can use it to discover data. You can use it to consume data. You can use it to not only just look at what data exists, but if you have authorization, or if it's publicly available, you can download that data easily. And at this point in time, I think DataLad indexes about 11 plus terabytes of data. And it's very likely that if you're looking for large-scale data sets, DataLad would be a very quick way of getting hold of data locally on your computer. It allows you to publish data. So all of you, if you said, raised your hand for Git, I'm assuming have also now interacted with GitHub. GitHub allows you to use Git to publish your code. You can use DataLad to publish data similar to how Git can be used to publish code with GitHub. In fact, you can put DataLad datasets on GitHub, assuming that the storage, the actual storage of the data is elsewhere. You can store it on GitHub, but that's going to cost you a little bit of a pretty penny, depending on the size of the data. It itself has a data portal, and actually before I get to data portal, I'll show you that. Reproducibility. So two recent features that were added to DataLad is the ability to say, I'm going to execute this shell command. And DataLad can track what inputs went into that process step, what outputs were produced, and track the provenance of it using the same thing that you were doing when you were using Git to track commit messages for your code. You make changes to your code, you say git commit, and you put a message. Using DataLad run, you can run existing tools on the data set that's under version control, and DataLad can track what step you ran and what steps were produced. You can, in fact, use it to even re-verify at a future point in time that if you rerun that same step, you're going to get the same exact output. So that's a quick way of getting to the three pieces we need, right? The data, the execution commands or steps that were used, and to verify that you produce the same output. The third piece that it has access to now is something called DataLad containers run. We weren't going to try that today if we get things working. But what DataLad containers run does is it can take Singularity or Docker containers, depending on the environment you're set up in, and actually attach your environment. Because effectively, those files are just another set of binary files. So now your data set can not only collect your data, it can also store the environment in which you ran an analysis. So let's take a quick look at the data portal, available data sets. And it's called datasets.datalad.org. So you'll see two sets of numbers shown under size. The number on the right reflects the actual amount of data that's indexed by DataLad, and that's 12 terabytes of data. DataLad, this server runs at Dartmouth, is not actually hosting 12 terabytes of data. It's only hosting about 286 gigabytes of data. That's what the number on the left says, how much of that data is actually present on this server. And the way DataLad does this is because it can point to a different resource. So if we take, for example, the Open Neuro data sets that Chris maintains, those are all accessible through a public Amazon bucket. So DataLad can simply point to that and say, if you need that data set, I can fetch it for you from there. So it indexes the metadata around the data set and stores that information. So let's take a quick look at one of these things. And yes? Is that better? Okay. Let's take OpenFMRI as an example. And you can now see the various data sets that are part of OpenFMRI accessible through this search index. And if I go into a given data set, this is not actually storing the data, but it stores the indices to the different elements of data in the data set. Okay, so we're, okay. We will assume that we can't do anything on the hub, which means we are going to improvise and try and see if we can do something on our computers. So first, let me just get a show of hands. How many people don't have Docker running? Okay, there's 1, 2 people. Is it possible for you to sit with someone who has Docker so that you can follow along? Okay. Follow along. You're trying to test this one? Okay. Before you use DataLad, we're going to try to do something else first. So we're going to switch it around, and we're going to build environments. And that will help us bring DataLad into existence on our computers. Now, for those of you who have Conda installed, actually, does everybody have Conda installed? Huh?
You want everyone to install Git Annex and DataLad locally?
That's not going to work on, because the Git Annex version is only available on the Linux.
Let's
Yeah.
try to pull down.
So maybe you can test that one, but in the meantime, I'll just go through the NeuroDocker steps first.
Okay.
Okay. So we've talked a little bit about environments, so I'm going to just switch it around. We'll get back to DataLad in a bit. NeuroDocker is a tool to help you create environments. Chris showed you, for those of you who went through the Docker tutorial, how to create your own Docker file. Right? And yes, if you can do that, fantastic. But there's a lot of boilerplate that involves in creating a Docker file for various kinds of software that you would want to install into your environment. The intent of NeuroDocker is to help simplify that boilerplate and provide two things. So it started support only for Docker files, but now it can also generate Singularity files. So you can use the same tool to create either a Docker file or a Singularity file, depending on the environment that you want to run things in. So what we will do is, fetch the latest version of NeuroDocker using Docker. The hub is a go? Okay.
Updated plan.
I don't know what I did actually.
Okay. I think everybody just stepped off the hub. No, I'm just saying. We will still go with the updated plan, perhaps, and then get back to the hub. We'll give the hub some time to breathe. Because creating environments is going to be part of this anyway. So let's go and create some environments. So let me ask a simple question. All of you, yes? I will expand it in a second, but I'm going to ask a question first. So you guys all pulled containers? Created containers? Pulled containers? What do you know is inside a container? Magic. That's precisely how most containers feel like when you pull them. Somebody may have told you that this container does X, but for most part, it's very difficult to know what's inside a container. You can see it. It's a file system, so you can easily see what's there. But it's very difficult to determine the intent for which that container was created or how it was created. So they become black boxes to a certain extent. And as Gael mentioned earlier, a container built today may not run a few years from now, depending on certain settings. So it might be nice to actually know how to recreate the container. And so NeuroDocker can help with that, because when it creates a container, it actually leaves trace of what it did to create the container. So even if the container might not run, you might be able to use what it did to create a container to rebuild the container. Now, this is not always possible. This depends on other tools and resources that are available. So let's take a look at NeuroDocker. Tal, is this large enough?
Yes.
Okay. So it's a command line program that helps you build containers. And since you guys don't have this image on your system, what I'd like you to do is to execute that first command, docker run --rm, and I will paste the link to this GitHub repo on the Slack channel.
So, Sarah, are we going to be building Docker with Docker?
Stop calling.
Are we building Docker with Docker?
Well, we'll be using a tool in Docker to build Docker.
A tool in Docker? Oh, this tool? I will explain in a second what that is. But I just want people to kind of start running it, because the first piece doesn't do anything. It helps everyone get this container on their computer. So I've pasted it in the NeuroHackademy Slack channel. It should be a fairly lightweight container to download. It doesn't actually contain all the imaging software.
Anyone run any troubles? Sarah?
And if you
No matching distribution. This is just regular.
So,
let me increase the font size of that terminal. Tal, can you see the terminal fonts? Pierre, can you see the terminal fonts? Okay. Now, if you wanted, we are going to run NeuroDocker through the docker run command, but it's also a Python package, so you can actually install it as a regular Python package and run it through that. However, it will still need Docker to actually build the Docker file, or Singularity to build the Singularity file. It doesn't actually build these things directly for you. So let's take a look at the set of things that it supports. So it's very brain MR imaging specific, as opposed to EEG or MEG or IEEG tools. However, if you knew how to install things to it, you could do one of two things. Send a pull request to NeuroDocker to add your favorite tool to it. Or, under certain circumstances, many of those packages, like M&E Python, is installable through a pip install. So you can use pip through NeuroDocker to install some of these packages. So those are things that you have to think about as you work with these tools. But in general, it supports most of the popular neuroimaging software and allows you to, instead of creating a Docker file by yourself as to how to install it, packages the boilerplate for installing these software automatically. So let's take a look at the prototypical example we tend to use, which is, we scroll down to Docker, and we can copy this. So the $sign simply represents the prompt. And let's take a look at what happens when we paste that command into the terminal. Okay. So I pasted this command under Docker into my terminal. So let's break down this command a little bit. The generate keyword tells NeuroDocker to generate a Docker file, to generate a file. The Docker keyword after generate tells NeuroDocker that I'm looking for a Docker file and not a Singularity file. The -- base says, if you've built a Docker file, you say from this base image, then do other things. So this -- base tells what that base image should be. So in this particular case, it's the stretch release of Debian. The one thing that you have to do still is know what package manager to use for a given operating system. There are two broad classes of operating systems that are supported: CentOS or Red Hat based operating systems, and Debian or Ubuntu based operating systems. So Debian and Ubuntu use apt, CentOS or Red Hat uses yum. And then the last piece over there says install ANTS, which is a neuroimaging software package, and install version 2.2.0 of ANTS. And once you run this, you realize that it generates a text file. Now, I could run this where I'm going to do this for a second. I then write this out. Let me just write this out to a Docker file. and I can look at this Docker file. So you can see that it says from Debian stretch, and then it has a lot of things that it puts in there. So it creates a startup script for you. It updates the installation, installs a bunch of default tools, and then it has a section where it's setting up ANS. And it's actually installing the binary release of ANS for 2.2.0. Now, for every single software that's available on NeuroDocker at this point in time, these argument options tell you the different variants of things that you can do. So for example, for ANS, you can compile it from the source on GitHub, or you can install a predefined release. FreeSurfer, for example, has one where you can install a minimized set of binaries if you're just doing recon all and didn't want the 730 binaries that normally come with FreeSurfer. So it allows you to customize your environment to what you need to operate on. And one of the best places to learn how to use it is to look at the examples gallery. So you click on examples gallery, and it will tell you things about very specific options that you can set for either Docker or Singularity or both. And then for every single neuroimaging software, so I'll take FreeSurfer as an example, it gives you an example of how you might install FreeSurfer into the package. Does anybody have any questions? Totally confused about what you're doing? This is the time to speak. Yes? We haven't actually built containers.
Okay, so
right?
then we're talking about installing FreeSurfer.
Right. So for the starting point, what we're doing is we're creating a file that will help us build the container. We're not going to actually build the container because if everybody downloads FreeSurfer right now, the internet is going to crawl. So we're going to show you how you might use this to build a container. It will still take some time. We can do it. We can test the internet. People up for testing the internet up here? All right.
So once we actually build it, then where is the container?
So I'm going to try building it on mine, and hopefully the internet actually does work. Yes? Okay, so there are two types of container. The question is, what is Singularity? There are two types of container technologies, actually more than two types of container technologies out there. But two popular ones are, one is Docker, which you all have been exposed to. The other is Singularity. Now, Docker, you will find that many HPC clusters at your institutions refuse to install and run. And that's because when you run Docker, you actually escalate the privileges of the container to root status. And system administrators don't like people to be escalated to root status at any point in time. The other piece is you could have a malicious container, and that could do things inside your system that is not good for the system. So most system administrators will say, we will not install Docker on our system. That being said, there are certain national labs which actually run Docker on their systems. They just control what containers you can run on the system. So you can flip it around as saying, I'm going to allow Docker, but I'm going to control the containers and what's used to build the containers in terms of running. Singularity runs at your user level. Yes, it escalates privileges at a few places, but that's very tightly controlled. So most system administrators are fine with installing, or I shouldn't say most, many system administrators are fine with installing Singularity on HPC clusters. And I think there was a thread I saw while I was away of an email thread and a link from the Scilab's website on how you might convince your system administrator.
Yeah, there's a link that's in the Slack channel of a template email if you need to send it to have them install it. Yeah.
But many institutions already now have Singularity running. And so just like there's some different underlying technological differences in how Docker containers and Singularity containers are built, the fundamental difference is Docker builds on what are called layers of layers that are piled up on top of each other, and it allows reuse of layers across common containers. Singularity images are single images that encapsulate an entire environment. But functionally or conceptually, they're similar in the sense that they both spin up an isolated environment that's separate from the actual environment you're working in with the pieces of software that hopefully are things that you need. So if we are going to build a container, which was the question, what I would do is to pipe that command to docker build. And I like to use a tag, so I'm going to tag it as NHAC, NeuroHackademy container, just for the moment. And put a dash at the end. Let me see if I can make this even larger. So all I've done is taken the command that we had typed earlier about installing ants and added on this piece. This pipe is a shell syntax for saying, whatever you produce by this command, send it to this next command. And if you want, it's actually in the original NeuroDocker page. If I go down to Docker, canonical example, you can see there's this pipe to Docker build dash at the end. So you can use that. The only thing that I'm adding onto it is I want an identifier for this container, and therefore I'm going to tag this with NHAC. The other nice thing I can try to do is to say, you know what, it would be nice to version this container in some way. I'm going to use this. I could use any other thing. I'm just using the date and timestamp to version the container for now. I could have simply said 0.1. One of the things you'll find in the Docker world is the use of something called latest. You download a Docker container, and by default, it'll download latest. You have no idea when that was updated, when that was changed. So if you're going to try and do reproducible things, it's important that you try and use versioned containers as opposed to something called latest. In fact, the version of NeuroDocker we are using over here is 0.4.1. So you can come back to that version in the future, even if NeuroDocker goes to 0.6 or 0.7 or 0.8. Okay. So if I do this, it will start building the container. Yes?
First we ran something without the Docker build.
Right.
What did that do?
So that would have just created an output text string, which is actually the contents of the Docker file. When we pipe it, it takes that content and sends it along to Docker to actually execute those instructions.
So do you actually have to run both lines of code? Or is that second chunk doing both at the same time?
The second chunk is doing both at the same time.
Okay.
Yeah.
So the first one was just a demo.
Yeah.
You actually want to do it with the work of both.
Right. Right. Any other questions? Okay. Let's see what speed at which it's downloading.
Do you use sudo?
Yeah, I use
She has permission issues.
On a Windows machine? Ubuntu. Okay. So there you would need sudo. Yeah. There are 2 Dockers. You could enable your user to have higher privilege by adding yourself to the Docker group on an Ubuntu machine, but okay. So this is where I have no idea how the internet connection is doing and how many people are actually doing the build. But effectively, this will build a container. In the meantime, while it's building, maybe we can just take a look at the examples. A little more. Before I take a look, I'll talk about one more feature that I'm not going to display over here, but something that might be useful to you later on. There's a project out there called Reproducible, which is very, very useful. It can help track what are the exact pieces of your file system that are being used when you're executing any command on the system. And what that means is one can use that project to minimize the size of your Docker container. So let's say you only need to do recon all from FreeSurfer. You don't need the entire package of FreeSurfer, which is about 8 gigabytes in size. The recon all piece of FreeSurfer is only about 800 megabytes in size. So you can use Reproducible to track a recon all step and then create a container that only has that minimal thing. And one piece of NeuroDocker helps you minimize containers. So this is not something that you need essentially. Most people today have fairly large disks. But if you wanted to distribute containers, you might consider distributing the lightest possible container for the application you have in mind, rather than the largest possible container. I think last year for NeuroHackademy here, we created a container that was 17 gigabytes in size. That's a fair bit of download for many things.
What was the tool you just
It's called Reproducible. And I'll pull it up. So if you go to reproducible.org, it will tell you. It's a very nice tool. There are constraints on where you can run this. It will run only on Linux environments as opposed to OS X or Windows environments. But most imaging tools run under a Linux environment. And in that environment, you can use it to do fun sort of things. So I'm not going to have you create other things. Let's see if that thing has finished. No, it's still downloading ends. So but we could take a look at one example, kind of more complex script that creates an environment. So this is using NeuroDebian as the base image. It's installing a bunch of tools, Convert3D, ANS, FSL, a GNU compiler, and other things into it. It's adding an entry point. So for those of you who use FSL on a Linux system, you have to initialize where to find FSL. Some cases it's made default by your system administrator that you can use, but typically it needs to find it. So it's adding to the entry point. It's installing a dev version of SPM12, creating a user called Neuro, and for that user, installing a mini Conda environment with a whole bunch of tools. This allows you to create fairly complex and custom environments, and this is the environment that's used in Michael's NiPipe tutorial, roughly speaking, that involves installing a bunch of different packages that can be then run with NiPipe. Okay. And there are Docker and Singularity versions of this. So all of these, one of the nice things about projects out there is you can look at examples. You don't have to kind of come up with how to do this. You look at examples and say, okay, how did they install these things? And I can go through it. The NeuroDocker examples gallery itself has examples for every single tool that NeuroDocker currently supports. And one of the latest additions, for example, this was added in, I think, earlier today, is VNC. So you can create a Docker container with a remote X server that you can then connect to from outside the container. So if you are running something like FSL View or Fossilize inside the container, you can do so without going through a lot of hassle that you would have to do to map ports and other things from inside the container to outside the container. Chris, I don't know if you talked about remote viewers in Docker.
Talked a little bit.
Okay. So this simply says if you're running a Unix system, we'll set up a remote view X server and you can connect to it. For example, for Chrome, I have an app, a real VNC app that I can use to connect to a Docker container running this. Okay, let's see how we're doing. Oh, I don't know if I can. I'm going to kill this. I think all of you will trust me if I say that Docker builds do finish once things are downloaded. And once things are downloaded, so in this particular case, I have a lot of other images, but you would see that tag that we created, NHAC, as being a tag of an image once it's created. It's not there right now because I didn't actually finish the build, but if I would have allowed ants to finish downloading, that's what would have happened. For those excited about this, we can let ants run, but it seems like we have access to the hub now. So, quick, yes?
So, for the examples that you gave in Docker, I imagine a lot of those, there's already Docker files that exist, right? But it's become more useful when you can actually add your own dependencies or kind of build upon it. So I guess there's an easy way, once it generates that text file with the standard stuff, to then kind of add to that or manipulate.
Absolutely. So the purpose of NeuroDocker is to create these specification files, whether it's a Docker file or a Singularity file. And you can modify them if you want. What we tend to try and do is to actually use NeuroDocker to add any additional instructions to it so that there's a single script that we can rerun to regenerate that file instead of creating something and editing it. But there are situations where you may want to add things. It would be good to know if you run into such a situation, post an issue, let us know, and we can try to see if A, it's a missing package, which would be easy to add, or if it's some construct that's missing that should have been there as part of support. But it's a fairly flexible tool to install all kinds of environments. And I hope you can use it to create different kinds of environments. I will talk about one thing in the Docker. So I did create this Docker file earlier. And if I look at the bottom of this file, it has this thing that it adds on into the container, which is basically the instruction set that it used to create this file. So that way, even if I gave you this container as a binary blob later on, you could come back to this and say, oh, I can recreate this container using this instruction set that's inside the container. So that's one way it at least tries to make the container not be as much of a black box as possible. But the world is moving towards an open container specification, which will make all of this a lot easier and transparent in the future. It's not quite there yet across all these containerized projects. Okay, any questions about NeuroDocker? Otherwise, we will switch gears and I'm going to check the hub and see if magic Ariel can see things on his computer.
Should be running.
Awesome. Great.
How did it become so black?
It's the dark theme. I mean, okay, it's under settings. Jupyter Lab theme.
Like I've learned something.
I mean, why would I use this when I can use this?
Well, there is actually a reason. You know that our eyes, when there's a lot of light coming in, they close the pupils, and you get a wider field of effective focus.
So if you're
That's it.
far away, it should be a brighter
So
screen.
it should be in better focus if it's dark on bright. It's basic vision science.
Ah. I do.
But it looks cooler.
The contrast, though, is a little better with light on dark. Focus, yeah. We'll do a psychophysics test next week. All right, so we have this, and now we can go to Files, click on Files, click on the Home icon. Can people read this from, or do I need to make it even large? All of you have it, so it's a little easier, even if it's a little blurry up here. We'll go to Reproducible Imaging, Notebooks, and Introductory Data. How are we doing on time? 4:25. Okay. We will go through DataLad, and then we'll take a 5-10 minutes break, and then come back and finish off with NiPipe. Okay. So normally I would say I wouldn't be using a notebook to do this, because I'm going to be executing shell commands in a notebook. It's really a terrible thing to try and do. Ideally, I would just have a set of things on my left and a terminal open on my right, and I would type these things into a terminal. The reason I'm doing this in a notebook is that people can look at this as a notebook later on and follow it. But it's really not the best use of a notebook. It's one way of doing things. And it actually asks me to do some crazy little things like help-np. Which is the non-paged mode of a man-page command. Otherwise, it gets stuck when doing it. Yes, Gaia?
Would we use a shell? Would that work?
So I could just hit terminal here.
No, but
Oh.
I mean, that's a general question. I don't know the answer.
Oh.
Would it be possible to use a shell engine instead of a Python engine?
We'll have to ask Fernando. I've never done a shell either without using %bash or this exclamation. I don't know if there is a shell kernel.
Oh, I think
There is? Okay.
There's a shell.
There is a shell kernel.
you can do all that. If this is all shell, you can save it in the shell.
Okay.
But you need to
I've never
install
used it.
kernel.
Ah.
That's the
No.
So yes, it's possible. Next time. So in the meantime, I'm just going to tell you a little bit about the syntax. This exclamation mark in the code cell basically tells Jupyter to execute the rest of the command in a shell. So you will see this coming up. So the first thing we'll do is just ask for help. And it gives help. And DataLad claims to do comprehensive data management. And it has a lot of different commands. And you can ask for information about these different commands as well. We're not going to go through all the commands that it has. But one of the things that we might want to do is to get a data set from somewhere. So we want to be able to install a data set from some remote location. And similarly, you can ask specifically for the help of this subcommand. All right. this is the other syntax of executing multi-line shell commands in Jupyter when you don't have the shell kernel enabled, which is to do %bash. It tells the executing thing, execute all of the remaining lines in the shell. And if we look at it, we are seeding to /data on the system, and then doing this thing called datalad install // I will ignore the warning that it gives for now. It has to do with Git configurations. And if you configure your username and email for Git, you won't get this warning. But for now, we'll just ignore that particular warning. And it installed OK. So that's the first line of this output. And we can take a look at this. So we'll use the tree command. And you can see that in that location /data, it installed a folder called datasets.datalad.org, within which there's a bunch of other folders. Okay. This didn't actually, it worked way too fast to bring in 12 terabytes of data to your hub container. It's not actually pulling in data, it's pulling in a metadata index to the data at this point in time. So the next thing we're going to do is try to see if we can do something useful with it, which is we're going to search for things. And you can, again, use datalad search --help-np to get the full help of the search command. And it says I need to provide a data set, and then I might make a query. So it goes through the whole explanation. What I'm going to do is to do a very simple query on a fairly popular data set that has been used by neuroimagers a lot, the Haxby data set. So I'm going to go to this line, and I'm going to, as you can see, it says datalad search, and it points to the data set location where I installed the meta or the super data set. And then I give it this key text string called Haxby. And I'm going to execute it. And it fetches a little bit of more information for each of the data sets that's stored in that location. And then returns this search. And it says that it finds the keyword Haxby across all of these different data sets. So since we like Chris a lot, we're going to do the next search by searching for his last name. It's also much easier to pronounce than his first name. And you can see that it quickly pulls up a couple of the different pieces, different data sets that are in this metadata. Now, datalad yet does not index every single data set that's on the planet. It indexes some data sets. And this is doing a search within the data sets that it indexes. So now we'll install a version of this data set. We used this at an IPIPE workshop last year at NIH called DS000114. And it's a very simple command. Datalad install, pointed to that data set. Again, that was way too quick for it to have pulled in a full brain imaging data set. Again, it does not bring in the full data set, so we can look at what it has. So that's the next exercise. We'll again ask tree, what do you have? And that looks like a BIDS-like structure, which you should all be familiar with at this point in time, because it is a BIDS data set. But it doesn't actually have all the files that are contained. And how can we do that? Well, let's try to look at one of the files that it's listed. So the dwi.bval is the b values of the diffusion file. And we're going to try and list the contents of the file through using the cat command. And it says, no such file or directory. And that's really the crux of DataLad. It's not actually brought in the actual content. It can fetch it, but by default, it leaves it where it normally resides till you ask it to get it. And that's how it's able to pull in that large metadata structure in, and so it gives you access to what is there to do search without actually pulling in the file. So the next step is to actually get the file. And it uses this line called datalad get. If I do that, it goes in. And now if I re-execute that cat command, lo and behold, that file has some numbers in it. Right? So 3 things. I fetched a data set, it did not get any files. I looked at the contents of the file, so it has the path to the file, but it doesn't actually have the content stored. Then I fetched the data remotely from remote, and then I could look at the contents of the file. And if you can keep that operation in mind, that's really the fundamental by which datalad and git annex does things. Okay. It also, so the next thing I'm doing is just doing an ls on that data set, and it gives me a version. Because effectively, it's versioning your data. What this means is, in the future, you would be able to pull specific versions of data from such a repo. So if you want, so an example would be the HCP project. The HCP project initially released 30 subjects. Then it released 100 subjects. Then it did 483 subjects. And then the full final data set. But along the way, it actually re-released versions of the data because it had to do reprocessing for some of the subjects. So some papers were published under certain versions of dataset. That's not the current version of the dataset. So if you wanted to replicate those papers, you would have to go and find that specific version of that dataset under which those papers were created. Something like datalad, even if you change, let's say, DICOM conversion, or if you're actually looking at MR sequences and creating new reconstruction algorithms that generate new versions of your DICOMs, you can store those different versions and can go back to any given state of the data set because you can version it just like you version code using Git on GitHub. So we're going to now quickly, for a couple of things, use the underlying command that datalad uses, git annex. And we're going to list this data set, and it doesn't do things. So turns out git and datalad don't recognize root folders without pointing to a particular data set. So this is a structure on the system. Just like your code directory when you use git has a .git in there, which stores all the metadata about your code, the objects and the references. Datalad has not just a .git folder, also has a .datalad folder that helps it manage these data sets. So you can see in the next one, we actually go to the data set. So we first cd to the data set, and then list things. This list tool or command is quite useful, because it basically says what is located on my system, what is available remotely. So you can see those 5 lines coming down from the top. those are 5 different locations where the data could be located. The X's specify where that file exists on a remote server. Okay. I'm going to skip exercise 6, which is just like datalad help. You're asking for help on the list command, and go to this place. So I'm going to now ask to list all the DWI files, and you will notice that dwi.bval exists here, but dwi.bvec does not exist here. And that's because a few steps back, we actually got the dwi.bval file using datalad get. So if I look at each of those columns, the X's say that that is present. So the first column is here, and it tells me. So what we're going to do next is drop the file, since so datalad drop now removes the file from locally. So let me give a practical situation where this might be useful. Let's say you want to do analysis on the HCP dataset, which has 15 million files. It's not available through datalad right this minute, but let's say it was indexed under datalad. You don't want to download the 15 million files from HCP. You may say, I only want the T1 files, or I want the T1 and the first resting runs. You would be able to get just those specific files using something like datalad, as opposed to getting everything, which normally happens when you go somewhere and go tar gz download, right? You get everything. HCP is not necessarily the best example because you can use the client to selectively search for things and create a tarball of just the pieces, some of the pieces that you need. But using something like this, you can get access to, I think on the Slack channel, I saw the HBN dataset, which is indexed by datalad. So those people who want to do things using HBN, you could use datalad to try and get pieces of the HBN. Okay, so let's now take a look at after dropping, what happens. That X is gone from here because it's no longer locally available. I have dropped it from my local existence. So this is why the MP3 analogy of git annex, or why it was created, is important. I don't want to listen to these tracks. Let me get rid of these tracks. It doesn't actually get rid of the data from the remote stores. It gets rid of it from my local store. Okay. So now we'll end up getting both of the DWI, bval, and bvec files. Datalad get DWI star. And it went ahead and fetched both of these things. Okay. How are we doing? Super confused, or this is so far okay? You can fetch data. You feel like you can follow some of these commands to get at other data sets that are available. Might be able to search for a few things, download the things that you need. So we're going to switch gears a little bit and create our own data set, because that's the other thing you often need to do, not just fetch public data. You've collected your own data. How do I create a data set that I can then publish and do things with? So creating a data set, you use the datalad create command and you provide a location. So I'm going to just say this is /data my dataset. Okay, so it created a dataset at /data /my dataset, and we'll add a dummy file to this. So I'm going to. So this has a little bit of shell syntax, but hopefully you're somewhat comfortable with it at this point in time. I'm just echoing a string of numbers to a file called 123 that I'm storing in the dataset. And so I create the file, and then I use datalad just like I can use git add to add a file to version control, I'm using datalad add to add this to the dataset. And now I can use git annex list to find out where that file exists. And as you can see, the only place that has X is locally, right? Because I created the file locally. It's not existent anywhere else. So git annex tells me you only have it over here. I can look at the folder containing my data set. And this is the crux of datalad. It uses what are called symbolic links to store the actual file under a content hash, and then uses the text name of the file to point to it. This is how it can drop that link to a file that doesn't exist because it's not there. So I can now try to cat this object that's inside Annex. So let's take a step back. When you use Git to store code, your code is in your directory, right? And various kinds of object states are stored in the .git folder. If I were to store data using Git, I would have two copies of data exist. One in your local directory, where that file exists, and one inside the .git folder. Now imagine your 1 terabyte file or your 10 gigabyte file. That will blow things up quite rapidly. By using symlinks, Git Annex solves that problem by saying, I only store one copy of the file, and that's in the .git Annex location, and I point to it from locally. So I can actually look at that actual file, and again, the cat command tells me what's inside the file, and sure enough, it's the 1, 2, 3 I had put in there. I can try to drop this file. Datalad says error, I won't drop it. And that's a protective mechanism. It's not going to drop a file it can't find a copy of elsewhere. If it were to be able to find a copy of this file elsewhere, it would allow dropping it, which is why we could drop those DWI files earlier, because the copies of those files existed on a remote server. But this file only exists locally. Now I can force it to drop it, and that's allowed, but by default, it'll protect you from erasing files that only exist locally. Okay. I can try to write to this file, and I'll say, nope, you can't write it. So by default, when you add something to datalad, it locks it as well from further modification. So to actually write to it, I will need to first unlock it, write it, and add it back in. Okay. If I try to write to it again, it will again complain because now I've added it back in and it's locked in.
Question?
Yes.
Keep track of the changes.
Yes. So if you were taking large files and making changes to them a little bit at a time, it will also blow up the state of things. So in that sense, it's like Git. It keeps tracks of changes. And you can reset the tree so that you remove copies of things. But typically, for example, the raw data, which is often the largest set of things that you have, is not changing. Right? And so that would likely not be a scenario that you run into a lot of the time. But yes, that's something you have to be aware of, that it does keep track of the changes. It's just like Git for data. But it doesn't do it very intelligently. So if you do make a change to a file, it's a whole new file that's created. And there are other mechanisms that they have backends for, which allow storing only the actual binary differences rather than all the changes. So let me go through this. So I had created this change where I unlocked the file, echoed 321 into the file, and then added it back in, right? And then I tried to echo 123, and I could not because it's locked. I look at this, my data set again, and now there is a very different MD5 sum because it actually has different content. Right? But this answers your question, which is I can look at the current content, which is 321, but the old file is also still there. So if I cat the old MD5 sum, I get the 123. And the entire history of the repo is available because this is just a Git setup. So I can do git log in this data set, and it tells me I added a file, I created an initial file, I modified the file. So you have the entire history of your changes logged in. So just as you were doing with code, now you can do the same thing with data using Data Lab. Okay, but let's do one last thing and then we'll take a short break. We want to run, I have a file, I want to run some scripts on it. So I'm going to create a silly little script which counts the number of characters in the file. Okay. So I create a directory, I write a script into it called run.sh. I change the executable bit on it. I can show what's in the script, and then I add this to scripts. Now note that unlike the previous add commands, there's an extra flag that I've added over here, and it's called toGit. So now I'm telling DataLad, add this to the Git repo and not the Git annex repo. So I'm treating this script as a regular text file in the Git repo as opposed to a data file that should live in the Git annex repo. Okay, it did that. And now I can introduce you to one of the most useful commands that they have recently added to DataLad, DataLad run. I know it's a little hard to see over here, the contrast. Maybe I should switch back to white, but only temporarily. So if you look at the command, the -m is a message that I'm giving DataLad saying this is what I'm doing with this command. And then I ask it to execute this command, bash -c, run sh on this file 123, and store the results of counting the number of characters in the file to a file called out. Okay. Fairly simple command, but you can imagine that the bash -c could be your most extensive MATLAB command or Python script, etc. And it ran the command. It says command start, command exit. So now I can go and do the same command I used earlier with git log on the data set. And you can see that the command is now encoded in the history of the data set. And it also tells you that a file called out was added into the data set. This is a little bit of git foo. So it's the --stat option of git log, which tells me a little more information than I get just out of git log. So it tells me what exact changes were created. But this is great. I ran a command, it ran on something, created a new file, and that file was automatically added. So now you have kind of a very bare bones provenance of a script execution on your data. So you not only have the original data that was indexed, the script that you ran, and the output that it created, all under version control.
And will it check out files that are not check out?
That are?
Will it get files that are not local?
That's an option. Okay, so I can look at this tree. So it obviously created this new file called out, the scripts. And what I can do, this is simply git commands that I'm using now. Git checkout head .. is effectively telling me what was the state of the repo 2 commits back. Okay. So if I run this thing and I'll parse the output, so it says 2 commits back, you only had 1, 2, 3 in your data set. But now you have 1, 2, 3, and you have the run.sh script and the out file that the run.sh script created. So this is how you know the entire state. And because this is a Git history, you can actually switch back to that point and get access to the state of the repo at that point in time. Okay. And I'm going to stop with this last one, because this is kind of the last piece of datalad run, which is datalad rerun. And what I'm asking it to do is to check out master, which is the current state of the repo, rerun, since allows you to specify a specific commit, and it will rerun all the steps that it took since that commit. And it will create a new branch in the Git repo called verify, into which it will store these things. So let's run this, and we'll take a look at it in a second. Again, the warnings are related to Git configuration, but it did run it. And now we can look at this with git log. So the little arrow going out, it says there are 2 branches. And so it actually created another out file in a different branch by rerunning things. And we can do a diff between these branches. So this is like saying, if I rerun the same code that I ran before, did it produce the same exact output? So go to dataset, I go to master, and now that I have 2 branches, I can use the standard git diff command to look at the difference between the branches. And basically the fact that it doesn't return anything tells me that those 2 branches contain the exact same content. So I will not do exercise 8. I'll let you guys play with it later on. Yes?
So you're inferring that there is no chain, or that the result is the same because the diff returned nothing?
Right. So if the content was different, git diff would have said these 2 files differ, or these files differ between these 2 branches. Now, you can easily imagine that in an actual imaging scenario, there could be various floating point differences in the outputs of the same scripts. So you would get differences in those situations. But there are many projects and programs which also create outputs which don't have floating point differences if they use the proper random seeds and other things. So in that case, you would get the exact same output. But if there were differences, you could also use it to see if those differences are within some tolerance that is okay with you. Or you could do more advanced things like looking at peak coordinates of clusters in those files if you're running an analysis similar to Josh's example that I gave earlier. So the basic idea here is that you can use datalad to version your data, track the commands that you're running on your data, track the outputs produced by the commands, all under version control. Now, Jarek told me to show something which I'm going to leave for perhaps next week, because it will require a set of interactive steps. Datalad now has something called datalad publish to figshare. So after you're done with your analysis, you could go datalad publish to figshare, and it will take this repo and create a tarball and send the information to figshare that you can then get a DOI for and put with your paper.
But that's like more like an export then.
Yeah. But it is an export with the full history.
But can you install from Figshare? Can you like use it like a backend, like S3? Or?
So in Figshare, it'll store as a bundle. Yeah. If you were to download it, it'll be like a tar of this local.
Everything.
Yeah. DataLad also has ways in which it can mark things as sensitive. So if you're converting DICOMs and storing it using DataLad, you can mark them as sensitive so that they don't get exported or published to a public location without your explicit permission. So it has a lot of different features that can actually help you to think about how to curate your data. But I think this tutorial was intended to demonstrate you can search for data, you can download data, and you can use DataLad to run some simple scripts to track things that you're doing on data. And if you understand those basic concepts, the rest of it will kind of fall into place. And DataLad does require Git Annex. I can't vouch for any Windows computers, but it does work on OS X and Linux. And Chris can vouch for Windows computers.
All of that.
Any questions? Okay. So we will take a 10-minute break, and then we'll come back and we'll finish what's called the NiPipe Quick Start. It's the fastest introduction to NiPipe. You don't have to do that because you haven't actually run it. Okay. And then in the notebooks, I'm going to choose Introduction, Quick Start, Non-Neuroimaging. Okay. But before I start, I should point out, Michael is in the room, and the NiPipe tutorial is maintained by Michael, and he's done an excellent job over the years of updating this, keeping it up to date, and making sure that it conveys the different concepts for people to start using NiPipe. So I'll show you the full page. Many of you have probably seen this. And it actually covers a lot of things other than NiPipe just to get oriented around the ecosystem a little bit. So for example, it does have introduction to BIDS, the tutorial data set. It has a little bit about NeuroDocker and Docker, Python, and then these two examples. We used to have only this non-neuroimaging example for the quick start, and very recently an imaging example for the quick start was added. Yes?
First of all, that's really small.
Oh. Okay, so let me go back to the notebook. So on the notebook, it's NiPipe tutorial notebooks, introduction, underbar, quick start, underbar, non-neuroimaging.
Thank you.
And if you slide it out, it shows the whole name. I'm going to slide this back in. Okay. I will tell a word or two about this official NiPipe tutorial, which is on Michael's GitHub page. So you can look at all the different concepts. We're not going to go through everything today in the quick start tutorial, but this actually goes through every single component and concept that's in NiPipe. So those are basic concepts. There's also workflow examples. These are focused a fair bit on fMRI processing. So that may not apply to some of the people who are not doing fMRI analysis. And that's one of the reasons the quick start tutorial we're going to deal with today has nothing to do with imaging. So just like I use DataLad without actual image files per se to illustrate the concepts, we're going to look at NiPipe in that same vein, look at things without thinking about the imaging pieces, because once you understand those concepts, plugging in the imaging pieces or interfaces is going to be fairly straightforward. And then there is a set of advanced concepts for people who actually want to contribute to NiPipe, like creating new interfaces and other workflows. So going back to this. Let me see how. So for those of you who are not familiar with NiPipe is a Python project. It's been running now for about 10 years. The current version of the code base, I would say, was created around 2011, and it has been refined, but the API hasn't really changed since 2011. So it speaks to the stability of the current API, but we keep improving things underneath it. And the general idea behind NiPipe was we often were running different kinds of tools. Whether here is just illustrating with SPM, FSL, and FreeCipher being three popular things. But if you think of the whole gamut of imaging, you often end up using certain kinds of tools that either somebody tells you this is a great tool to use, or you have a specific need because a certain data set that you've generated requires that tool. So you might be dealing with ASL data, and that might require a tool from UPenn. You might be dealing with some kinds of diffusion MRI, and that might require DMI-Pi, etc. And the problem was that you had to learn these tools, which NiPipe does not reduce that problem. You still have to learn how to use the tool. But you also have to learn different kinds of interfaces. So one tool might be an executable in a command line. The other tool might be a MATLAB script. The third tool might be a Java command. And so you all had to go and learn these different ways of interacting with these tools. What NiPipe did was said, we will write Python wrappers around these tools and give you a consistent way with which to call these tools. Okay. So that was step one, which is the interfaces. It provides this uniform Python API. The second piece is, once you have these wrappers, you can now construct workflows which put these tools together with some nice semantics so that you don't have to do data management. Because often when you're running multi-subject workflows or comparison workflows of various kinds, a lot of your scripts end up saying, this is how I'm going to look at data organization or create data organization or naming things. NiPipe is a data flow framework, which means you say what are the operations you want to conduct on the data, and NiPipe underneath handles how it names things, creates outputs, and moves data between things. And finally, the last piece of the NiPipe code base is execution plugins. And this is just a subset of things that are available, which is you might be at a university cluster which is running SGE, or you might be at a university cluster that's running Slurm, or you might just have your local laptop which doesn't have either, but you have multiple cores running on it. So we can switch plugins quite easily given the data flow structure and say, oh, I want to run this locally on my laptop, or I want to run this on the cluster using the Slurm queuing system, or I want to run this using SGE or PBS. Okay. So I've been told that you guys are somewhat now familiar with Python, if not people who are experts at Python in the room. So I'm going to assume some Python knowledge at this point because we are going to dig into, but these examples should be fairly straightforward to illustrate kind of the semantics of NiPipe without bringing in the neuroimaging tools. So the first thing we're going to do is to import a few things.
And if you get stuck, raise a hand and I'll come over.
And there are actually multiple people in this room who can help. So Michael is over there and Pierre can help as well. Back there. Okay, so the three things we have imported from NiPipe are workflow, node, and function. And in this context, function is a function interface. It allows you, just like we were wrapping external tools, function interfaces allow you to wrap Python functions that you write in Python. And the reason you want to wrap some of the things is, again, because you might want to execute not just locally, where you could have just passed the function, but you might want to execute on a remote cluster where the nodes are disconnected, they don't share memory. So something has to save the information, send it out, and do things. So we're going to take a very simple function here. Sum of two numbers, right? Fairly straightforward to write. And we'll create a workflow. In NiPipe, we name things. So workflows have names, nodes have names, because the actual variable that Python uses makes no sense when you're sending things to different pieces. So we refer to a lot of things using the names we assign to them. So in this first example, we create a workflow called hello, and we create a node which wraps this function interface. And we tell this function interface, hey, this function takes two inputs, A and B. It creates an output called sum. Here's the actual code for the function called sum. And I'm going to name this node A plus B. Now I can set the inputs of this function. So I can set adder.inputs.a equal to 1, adder.inputs.b equal to 3. I add the node to the workflow. So the workflow is a container object. You add the node to it. I set a base directory, and I go run. I hope 1 plus 3 is 4. And if I run this little thing, and I look at the output of the workflow, which is this execution graph, and I look at the nodes of the graph, I see that the one node that exists in the execution graph gives me an output with sum 4. Okay. Single node workflows are not very useful in most cases. Yes? No, nodes can take any interface. I'm using a function, so it could take, for example, SPM interface for segment, or it can take recon all from FreeSurfer. So nodes wrap around the various actual tools that you want to use. I'm using the function interface for this example because I didn't want to bring imaging tools into this particular example. But if you want, if you click on the other example, which is the neuroimaging example, all of the interfaces used there would actually be imaging interfaces. But that example will also take a little longer to run because it runs on real data rather than these toy inputs and outputs. Okay, well, I've got one node. Let's create a second node. So now I define a second function. It's called concat. And all it does, it's concatenates A and B. It's a simple Python function. It takes two things and returns a concatenated list of those two things. And just like before, yes. So for the moment, we like it that way. But from a control perspective, you can set the logging level to critical only, and it will suppress almost everything except when it runs into errors. So I define a new node called concater. And just like before, it's a function interface that I'm using. I set its inputs. It has two inputs. And I set an output name, sum list, the function, and I call this node concat A comma B. And now comes one little trick, which is I need to connect the output of the first node, because what I'm trying to do is this two-node workflow where I send the output of the first node into some input of the second node. And that's this connect statement. So it takes the adder node, and the adder node, if you remember, had its output called sum. So I'm using this